I'd like to welcome all of you, those online and here in person, to today's presentation on machine learning. A quick note for those on the webinar. If you'd like to ask Rick Hamilton a question, please submit it via the chat function at any time during the presentation. We will collect these questions until the Q&A period begins at the end of the presentation. We will get to as many questions as we can during the time we have. And now, I'd like to introduce Rick Hamilton with Optum. Rick works broadly across strategic imperatives, including machine learning, genomics, blockchain, Internet of Things, and cybersecurity, to help people live healthier lives and make healthcare work better. With over 845 issued U.S. patents, he was formerly the most prolific inventor in IBM history and has completed engagements involving cloud, artificial intelligence, Internet of Things, and innovation invention strategy in 30 countries. He is currently an American Association for the Advancement of Science Lemelson Foundation Invention Ambassador. Today, he will provide an introduction to machine learning and artificial intelligence. Rick, the floor is yours.
Great. Well, thank you very much, and thank you to those here in the room as well as those listening in from afar. My name is Rick Hamilton. I am, as Kelsey said, a longtime IBM inventor working with a variety of emerging technologies. Earlier this year, I made the move to Optum, where I'm delighted to continue to work with a variety of emerging technologies. Today, we want to talk about machine learning and AI, but to really get there, we need to start by understanding the context, because there's a confluence of a number of different technologies that are converging today. And I would argue that machine learning is not so much a case of technology pulling us down a path as it is an imperative. It's something that we have to do to master the data that's being thrown at us. And it's really the only way that we're going to continue getting insights as the data volume and velocity and variety continues to grow. So for the first few minutes, we'll talk a little bit about how we got here. So some observers today are saying that we're in the midst of a fourth industrial revolution. If the first revolution was mechanization, it was applying water power and steam power to replace muscles. The second was really the rise of electricity. We saw mass production assembly lines come into being. The third revolution occurred in our lifetimes and those of our parents, as computers changed the way that we work, we live, and we play. And today we're seeing the advent of cyber-physical systems. And by cyber-physical systems, we're talking about the introduction of processors. We're talking about the introduction of software into the very fabric of our ambient environment. And so as these processors take their place among us in our everyday world, all kinds of new possibilities are opening up. So how did we get to this place? Really, it's an explosion of multiple technologies. You know, the big companies, your Facebooks and Amazons and Googles and Microsofts, are turning out new innovations almost daily. And as they turn out innovations, we as consumers, we as professionals are asking for more processing power. We're asking for more connectivity. We're asking for more storage and memory. And as these things are delivered to us, it gives a rise for all these technologies. And so we are in a spiral that I would argue is a virtuous cycle, but I don't know, have me back in 10 years and we'll look back and figure out whether or not it was virtuous. But I still believe it is. There's also another factor that weighs in heavily in the conversation today, and that's the rise of cloud. Because cloud has certain attributes that are great for business, but don't really pertain to machine learning. Then they have other things that are very much associated with machine learning. Some of the things you think about with cloud are changing economic models. We can now lease computational cycles by the hour, by the day, by the month, instead of buying big servers that are mostly unused. That's not very relevant to machine learning. Something else that cloud gives us is, I would say, elasticity for our businesses. Our businesses can become more agile. We're able to adapt more quickly to changing business conditions. Again, interesting, but not so much about machine learning. But there are other two factors about cloud that very much are pertaining to the topic today. One is that the first generation of the internet gave us the ability to find out information from any point in the world. What cloud gives us is the ability to get high-value services from any point in the world. So whereas 20 years ago I might have used my Netscape browser to go off and find out Australian rule football scores from Perth just because I could, I mean, that was interesting, but now I can get machine learning services from AWS. I can get them from Google. I can get them from IBM, all because of new cloud capabilities being delivered. So that is very relevant. The other thing that I would tell you that cloud has done for us is to help with data liberation. And by data liberation, I mean, it used to be that data was behind the walls of these big corporate data centers, but now data is everywhere. Data is accessible. And so at least technically, we no longer have these barriers to getting the data that we need like we did in the past. And this, likewise, is very relevant to machine learning. We've seen an explosion in connected devices. That's no big secret. The first thing we think about is our telephones. But the fact of the matter is, it's more than that. Really, we've seen the rise in machine-to-machine communications. And these are one machine talking to another and reporting on what's happening in the world. And so this is not just happening in one area, but in many different areas. There is some speculation that we may not hit 50 billion by 2020. The number may be closer to 40 billion devices, but nonetheless, it's a tremendous growth over the course of maybe 15 to 17 years. On top of that, of course, we have a corresponding growth in information flow. And so you see here over the course of 13 years, we're looking at roughly a 41x expansion in the amount of information flowing over the internet. This isn't a story about slow, predictable growth. Rather, it's frankly a Cambrian explosion. Sometimes it's geometric, sometimes it's exponential. The challenge that we have increasingly is how to tap into all of this. Cisco, the networking company, says that the highest growth traffic category is actually a machine-to-machine. Again, this is about devices that are creating information about the world around us. So this presents a challenge and an opportunity. It's a challenge because trying to get your arms around this much data is very difficult, but it's also an opportunity because whoever can find the data that's needed and leverage that data creates all kinds of possibilities. So this brings us down to the central question of why machine learning. You know, as data flows from nearly every device, we're replacing approximation and guesswork with precise information. This isn't just happening in healthcare. It's not just happening in retail or financial services or media and entertainment. It's happening everywhere. And so the question that has to be asked then is whether or not our supply of programmers, our supply of technical talent is keeping up with this growth in data. And I would tell you, we can go knock on every door of every university around the world and try to find people to go off and write deterministic programs, but we're not going to be successful. We need a new path forward. We need a path that has systems that can grow with the data, systems that can begin to predict and prescribe, systems that can increasingly make autonomous decisions. And that means the only way forward to leverage this data, the insights that we as a society need, is to use increasingly sophisticated learning systems, which is what brings us to our conversation today. You understand, this is not just a matter of somebody saying, hey, we've got some great new advances, we need to put them to use, but rather it's this realization that there is no way that you and I can sit and go through all this data and figure out what it means. We need new paths to conquer these mountains of data. So we want to talk now. And by the way, I'm going to slow down at this point because now is where it gets good. We're going to talk about three terms, and we're going to go into a little bit of detail for each. The first thing we're going to talk about is artificial intelligence. And then we're going to get a little bit more specific. We're going to open up that doll and look inside. We're going to find the second doll, and that second doll is machine learning. And then once we go through that, we're going to open up the third doll, and the third doll is deep learning. And we're going to talk about what each of these terms mean and what they might mean to you and the way you do your job. So artificial intelligence is a very widely used term. I probably use it 20 times a day, but frankly, I'm not really crazy about it. It's a very fuzzy term, and it encompasses a broad range of capabilities. Very generally, it refers to anything that a computer is now doing that used to be the domain of humans. And so if a computer starts doing something new that's human-like, we often will call it artificial intelligence. And so that's fine, that's okay. But the challenge is that the term AI really constitutes a moving target or a moving border. In fact, decades ago, some computer scientists referred to compilers that compiled your code down in a machine language as artificial intelligence. And the reason is because for the first time, computers were speaking their own language, and so of course it's AI. But of course, as time goes by, we begin to use a technology more and more. We stop calling it by this general AI term and start calling it by a specific name or by a brand name, for instance. And so if your spouse asks you, what time does the SunTrust at Barracks Road Bank close? You're not going to say, let me go ask my artificial intelligence. You're going to say, I'll ask Alexa. And so artificial intelligence becomes part of the background of our lives day in and day out. And we stop calling it AI, but instead pick up new names for it. But that said, the technology is still valuable. But when people talk about AI today, what they're mostly talking about are the excitement, is the excitement and the advances happening in machine learning. So let's go into machine learning a little bit more. Machine learning is a term that was coined back in 1959, I believe it was, by an IBM engineer. And in this, what we mean is systems that learn from the data without being explicitly programmed to deal with all possible inputs. And this is a valuable idea, a valuable concept. There was a wonderful but sensationalistic cover story on Wired magazine last year. And the big sensationalist part was it said, the end of code. And underneath it, it said, soon we won't be programming computers, we'll be training them. And so I hate the end of code because code still goes into everything, but it was very true that increasingly we will train our computers the same way we would train our pets. And this is the transformation that we're under right now. Now, I want to show you some ideas, and I'll say you need to hang on to this, you need to keep this with you, and other ideas I'll say don't worry about memorizing it. So the first thing I want to show you is something I'll say don't worry about memorizing. We have up here 5 different kinds of machine learning, their favorite tools. The reason I give you this information is so that you know machine learning is not a monolithic category. If you say somebody's doing machine learning, the question you should ask is what kind? Because there are different tribes. One tribe is Bayesian, and Bayesian's favorite tools are posterior probabilities. You have the symbolists who use logic and expert systems. Sometimes the symbolist will be referred to as using GOFI, or good old-fashioned AI. This is if-then-else kind of syntax. A third kind of machine learning comes from the analogizers with support vectors, or SVMs. A fourth kind are the evolutionaries. Genetic programs made a huge splash in the 90s. There was a lot of work that happened there. And then the fifth tribe are what are called the connectionists, who deal with artificial neural networks. So again, don't be too concerned about the specifics on this. But again, I want you to see this is a heterogeneous field. If you do want to know more about this topic, I'll give you a recommendation for a book. There's a wonderful book by Pedro Domingos, who teaches computer science at the University of Washington, called The Master Algorithm. And so if you want to know more about all these different kinds of machine learning, pick up The Master Algorithm by Domingos. So that was the part I said I wouldn't spend too much time talking about. There is something here on machine learning, however, that is very important. And I would argue that if you take anything away from today, maybe this is what you need to take away. There are 3 fundamentally different approaches to machine learning that we're going to be going into. And to make this even more complicated, these 3 different approaches can be used to varying degrees with these 5 different tribes. And so you get a lot of complex permutations very quickly here. But let's talk about the fundamental approaches to machine learning. One is what's called supervised learning. And in supervised learning, you have a target or value that exists, which you can put out there, and then the system tries to predict when that target is going to be seen. So for instance, working in the healthcare space, you might have a set of 10,000 pictures of tumors, and you might use these to train your learner how to spot a tumor. And so that would be supervised learning. Likewise, cat pictures, can be used to train supervised learners. Whether you know it or not, you almost certainly have trained supervised deep learning systems before. If you've ever uploaded a picture of your spouse, of your kids, onto Facebook and tagged somebody, what you're doing is providing reinforcement. I shouldn't use the word reinforcement. What you're doing is providing data for a supervised learner to understand that. And so after doing this a few times, the system says, do you want to tag John? Nobody has written code that says, here is John's nose width, here is John's hairline, here are John's ear shapes. Instead, the system learned it through a supervised approach. So that is the first and least complicated of the 3 approaches to machine learning. The second approach is what's called unsupervised learning. And unsupervised learning is where no data target or name exists. It's unlabeled data. And this is something we could all understand very intuitively that computers would be very good at. Because if you hand me a terabyte of data and say, Rick, find the patterns, I'm not going to be too good at that. But computers are very good at poring over the data and finding where patterns exist. Think of this often as sophisticated cluster analysis. So when you use unsupervised learning, there's a couple of different things that may happen. One is you get red herrings. These are hallucinations, sometimes caused by overfitting. But what you see here is a computer coming back and saying, it looks like people born on a Monday have a 7% higher chance of large cell carcinoma than people born on Tuesday. You could apply the human sniff test to it and say, no, that's garbage. There's nothing here. But what you can also get are valuable insights from unsupervised learning. If you find out that a certain kind of profession seems to have a 13% higher incidence of a certain kind of leukemia, maybe there's something here. Maybe there's some kind of environmental exposure that needs investigation. But unsupervised learning is very broadly about turning your learners loose on a big set of data and seeing what kind of insights it can deliver. And then you, as an individual, often go back and look over these results and figure out which you want to pursue. So that is the second kind of machine learning. The third approach is what's called reinforcement learning. And reinforcement learning is all the rage today. Reinforcement learning is where your system chases a nominal objective or chases a goal. And so the two places that reinforcement learning are really making a splash today, one is in autonomous vehicles, and the other is in game systems, which we'll talk about both of these. So if you think about the way a reinforcement learner might work for an autonomous vehicle, you say, well, I have to give my AI a goal, so I'm going to give it the goal of getting me from point A to point B as fast as I can. And so what's the AI going to do? Your learner, it's going to try to drive a straight line from point A to point B. And that's not going to work so well. Fortunately, these things are trained in computer simulations before they ever go out onto the roads and the wild streets of Manhattan. So then you say, well, I need to construct my goal, my objective for my autonomous vehicle with a little bit more precision. And now you say, well, I want you to get me from point A to point B as quickly as I can, but follow the rules of the road. And so you can download the databases from a GIS table, and your system, your car can begin to drive on the road. But maybe it doesn't understand the rules of physics and that you can't drive right through another car. And so you can imagine that you've got to actually construct some pretty sophisticated goals and objectives here to get an autonomous vehicle to work right. So that is one example of reinforcement learning. I mentioned another example that's very big these days is in teaching systems to play games. So there was a game back in the late 70s, early 80s. I had forgotten about it, but it was called Breakout. And Breakout was where you had basically a ping pong paddle and you try to hit this ball into a brick wall. And when you hit a brick, the brick disappears and you get points. So there's a fascinating YouTube video. I'd urge you to go out there. It's only 2 minutes long, of an AI, of a reinforcement learner, figuring out how to play Breakout. And initially, it knows nothing about the game, but it was given the simple goal of maximizing its score. And so early on, you've got some random movement of the paddle, and it figures out that if the paddle hits the ball goes up and hits a brick, and it gets points. So over the course of 4 hours of actual training, the system went from completely incapable of playing the game up to mastering the game and figuring out every time it's going to get a hole right in the corner, get the ball up behind the wall, and really get these incredible scores. As my kids would say, to beat the game. Another example of gameplay today of reinforcement learning is with AlphaGo. For those of you in the room, are you familiar with AlphaGo? Okay, we got some shaking and some nodding both going on here. Okay, so Go is, of course, a millennia-old game that is very complex. It makes chess look like a very simple game in comparison. And there have been predictions that it would be many years before any system, any computational device could beat the human Go champion. Well, guess what? The human Go champion has been beaten. And so AlphaGo was developed by DeepMind, which is a division of Google, based out of the UK. But what has been interesting is that it was a reinforcement learner that was actually trained against humans, and it basically revised its approach over time, and it developed a very sophisticated way of playing this game. I wish I knew more about the game. The people that actually do understand it say it's like watching poetry in motion, because the system will make moves that nobody can figure out why, not even the world champion, but the logic will all come clear a few minutes later when the system actually does something very decisive. The thing which is fascinating, though, is that there is a new version of AlphaGo. So it was only in the last 8 months or so that the old system beat the world champion. That version was trained against humans. There's a new version out that was trained by playing the first version. And so this is an AI that's been trained by AIs. So there were 100 Go matches have been played between the version that beat the human champion and the new version. The new version won 100 matches, lost none. And humans watching this are often dumbstruck to say, what is going on here? We don't understand why these moves are being made. But it's a case of AIs, again, learning from AIs. So let's get back to the concept of reinforcement learning. Everything is about the goal. It's about the objective. And there is a great deal of thought and a great deal of writing right now going into this question about how do we define well-intentioned and really positive goals for these learners as they become more and more sophisticated. So we've talked about AI at a very broad level. We've talked about machine learning. We've got different tribes of machine learning. There's three basic approaches. We said supervised, where you've got basically labeled data, unsupervised, where the data is not labeled, and then reinforcement learning, where you're chasing a goal or a pattern, or chasing a goal or objective. But there is one of these schools of machine learning, we talked about the connectionist, that's getting a lot of airplay these days, and that is this concept of deep learning. Deep learning is state-of-the-art connectionist technology, and it is roughly inspired by the human brain. I feel like I'm in the right place to be having this conversation today. If anybody ever tells you that artificial neural networks mimic the human brain, roll your eyes, because they don't know exactly what they're talking about. Instead, it's inspiration, it is not mimicry. What this comprises is an input layer, an output layer, and some number of hidden layers. The number of hidden layers can be very, very deep, which is why it gets the name deep learning. So let's talk about the way that this works at a very high level. Each of these layers in a deep learning network will put increasingly sophisticated structure around concepts or ideas. And so if you were to have, say, a deep learner with 7 or 8 or 9 layers that is doing image recognition, maybe the first step is that the image data comes into this artificial neural network. The first layer may say, I detect patterns of light and dark, and it will pass that information to the layer behind it. The next layer will say those patterns of light and dark comprise edges, and it will pass that information to the layer behind it. The next layer may say those edges are roughly spherical or circular in shape. Pass that on. The next layer says that sphere appears to be an animal head. The next layer says that's a cat head. The next layer says, oh, that's Rick's cat Fluffy. And so that is the way that an artificial neural network basically processes data, with each layer becoming increasingly sophisticated and making more and more, I would say, human-like interpretations of what data is out there. There's several reasons why deep learning is booming these days. Let's talk about each of these. The first reason is that to do supervised learning on deep learning networks, we need data. And as we said before, as we saw before, the amount of available data is going through the roof. And so all this data that's out there, whether it's social media, whether it's image files, whether it's reams of patient information, can now be sucked into deep learning networks, which is making them more and more powerful, and in turn, more and more likely to be used. A second thing that we've seen in terms of why deep learning is taking off is because of the advances in processors. The original concept of an artificial neuron was developed by Rosenblatt in 1957. In the 1960s, these were fleshed out and made into something that was called perceptrons. However, they weren't very successful. Over the course of time, we realized that conventional CPUs, think about the Intel processor in your laptop, they don't do these artificial neurons very well. So they looked for things that could do artificial neurons very well. There is a company called NVIDIA. Has anybody here ever heard of them? Okay, a few people nodding. NVIDIA makes graphical processing units. And back, say, 15 years ago, these were something, I'm an electrical engineer with 9 years of engineering school. For me, it's like, who cares? The GPU is just something that sits inside your computer to help your graphics render. The only people who are really into GPUs were serious hardcore gamers, because they could go out and get these supercharged GPUs and render graphics even better. But NVIDIA really had a big stronghold on the market in GPUs. But in 2009, there was a seminal paper that came out that basically figured out that GPUs were ideal for doing deep learning. And so what's happened, NVIDIA has suddenly got really the lion's share of deep learning processors that are coming out today. And they have a stock price to match. MIT's Technology Review magazine, which lists the 50 smartest companies every year, just this year, a few weeks ago, listed NVIDIA #1. NVIDIA is investing billions of dollars in fleshing out new topologies and new architectures around GPUs for deep learning. The other thing is we're seeing increasing numbers of application-specific integrated circuits. Companies like Google developed their own chips for doing deep learning. So Google has something called a tensor processing unit, or TPU. The good news is you don't have to go out and buy a TPU. You can get their service called TensorFlow right over the web. And so companies, again, like Google, Amazon, IBM, are making machine learning capabilities available to you wherever you happen to be. A third reason that we're seeing an explosion in deep learning right now is because of architectural approaches and software embodied methodologies. And we've had some great advances in the last few years. And I will have to speak candidly here. I wrestled with whether or not to try to go into this level of detail, but I'm feeling ambitious today, so I'm going to try to go into this detail and give you a little bit more information about how this network actually learns, how this network actually works. And I'm going to try to do it without math in 3 minutes or less. And I say without math because the math gets into differential calculus and n-dimensional matrix manipulation in the first 10 seconds. I don't feel like going there this afternoon, and I don't think you want me to either. So let's try to give you, in just a few minutes, some high-level pictures of how this learning actually occurs. So look at this picture of these hidden layers of an artificial neural network. To start thinking about how it learns, just take one neuron, one node, and look at what's happening there. We have one or more inputs. These are signals coming in on neural pathways, and one or more outputs going out of the neuron. So each of these neural pathways has a weight associated with it. And this is not rocket science yet. If you've got a signal coming in on a neural pathway with a big weight, that signal counts a lot. If the weight goes to 0, you can probably throw that signal away. Okay? Simple enough. The output of each neuron is the summation of each of the weights times the signal on it across each of the paths coming in, plus some bias value, which is passed through what's called an activation function. You can ignore that for now. It's basically a fancy function that turns on or turns off the neuron. So there's two things that you need to take away from this. One is that these neural pathways have weights. That's important. The second thing is I mentioned a bias function, or a bias with each of the neurons. So these are variables. And in order to understand how we actually learn, you start to get this picture of a neural network as being a wall full of knobs. And you can turn these knobs, and the knobs you can turn are the weights of the neural pathways, as well as the biases associated with each of these neurons. So now let's widen our aperture and think about the overall network itself. If you have a network that you want to begin training at the very first onset, the weights on all these neural pathways are going to be set to random values. I don't think it's going to work very well, but no, it doesn't work very well. The biases also for the neurons will often be set at some sort of static value, and so that's where you begin. We often think of deep learners as giving you a binary output. Is this a cat picture? Is this a tumor picture? But I hate to say it, but trust me on this, we can also predict for known data a mathematical output that we want to see from this network. And so if you're feeding certain kind of data in, you can say we want to see certain numerical values out. So you pass the data in, and you get a terribly wrong answer on the output. And that's okay, because we can use the chain rule from calculus to go back and identify which neuron, which neural pathway in here gave us the greatest contribution to that error. And so we've passed the data through once. Now we say the big problem occurred here. And we go through, we adjust the weight of a neural pathway. We adjust the bias value on a neuron. Now we run the data through again. We figure out where now is giving us the greatest contribution to the error. We adjust the weight. We adjust the bias. So this method of changing weights and biases is called gradient descent, and it's at the heart of deep learning. We also have a technique called backward propagation of errors, or sometimes called backprop, which traces the data backwards. It's all about figuring out which of the neurons is giving us the most error component and which of the neural pathways is giving us error component. You do this many, many, many times, And each time, this output gets closer and closer and closer. When you get it so that the output error function is down to a minimum, at that point, the network is trained. And so this hopefully has shed light on the fact that when you train a neural network, you're really simply adjusting knobs one at a time, one at a time, one at a time, and you are making the network perform better and better and better to predict what you need it to predict. Now, this is a powerful idea, and it creates great value. But I would point out also that there is something called the explainability problem in deep learning. Has anybody heard of this? Not okay, a few people have. So explainability problem is really saying, how do you explain how a decision was reached by this network? So let's think about a different application, maybe financial services. I run a bank, and I'm going to fire my loan officer and use a deep learner to do loan processing. And so I train it. I'm going to use a simple example, 10,000 people who are approved for loans, 10,000 people who are rejected for loans. I train my network. I adjust all these knobs. And now the network makes perfect decisions every time. Okay, so Rick Hamilton goes in, applies for a loan. Rick Hamilton is denied. And I say, well, why did you deny me? It was because of my race, my sexual identity, my religion, wasn't it? And you say, no, it wasn't. And I say, well, why did you deny me? You can't really explain why I was denied. The pithy answer becomes, it's because our AI overlords told us to deny you, Rick. The lengthy answer is that we trained a network and we set values for each of these neural pathways, and we set values for each of these biases and neurons, and when we pump your data through there, it's said to deny you. And neither one of these answers is really going to make me feel good. And so there is a move afoot in certain national governments, for instance in Europe, to say that if you are using neural networks for some kind of sophisticated decision processes, you need to be able to explain how those decisions were reached. So we made it through the ambitious target of explaining how neural networks actually operate. So this is really the source of great buzz today. A lot of the great deal of progress we've been seeing is that we've gotten very good at these enhancements that we talked about before at the very end here. It's about quickly making decisions and quickly training networks to get usable results. So the next question you might ask is, well, Rick, you said you didn't like the term artificial intelligence. Is this really AI? Well, the answer, of course, goes back to, what do you want to call AI? The fact of the matter is that there are a lot of things that we use every day that could be considered different kinds of AI. These are all forms of weak AI. And when we talk about weak AI, we're talking about computational systems and learners that do a very narrow task. And they may do the very narrow task very well, but AlphaGo is not going to drive my car, and neither is that breakout playing game going to pick the stocks for me. So there is, in fact, a push among some researchers to go more and more towards strong AI, sometimes called artificial general intelligence. I would say for most everybody on the phone and most everybody in the room, this is of little clinical relevance, but it is a very fun concept to explore intellectually. The idea of AGI, or strong AI, deals with the concept of creating a very flexible learner, a learner that doesn't just figure out how to drive a car or play a game or recognize cats, but instead that can do many, many things and take on human-like intelligence. Of course, there is also the possibility as well of taking on superhuman intelligence also. And so we've seen over the last couple of years such luminaries as Elon Musk and others warn us about the dangers inherent in these kind of AGIs or strong AIs. I would tell you again, I don't lose much sleep over what an AGI might do. But if you want to explore this, again, it is a very interesting intellectual concept. There's two books I would recommend. One is called Superintelligence by Nick Bostrom. Superintelligence, Bostrom is from Oxford. His book came out in 2014, I believe, and it was a highly recommended book by Bill Gates. I think it could have used an editor. It's been about 80 pages shorter. I would have thought more of it, but it's still got a lot of great insights in it. There's another book by Max Tegmark. Max Tegmark teaches at MIT, and he wrote a book either late last year or early this year called Life 3.0, Life 3.0, and it really talks about matters such as how we create these super learners, these AGIs, and also what it means to be conscious. He has some interesting theories on consciousness, that consciousness is achieved through certain kinds of sophisticated information processing, and therefore it is substrate independent, and that we as carbon-based life forms shouldn't be too comfortable in our belief that we're the only ones that can experience consciousness. Again, a bit of an intellectual curiosity here, but if your interests go there, those are two books I would recommend. So I want to turn our attention now to how we apply this in the healthcare sector. And since I've only been in healthcare for about 7 months, there's a good chance that some of you in this room or some people on the phone would know far more about this topic than I would. But I do want to explore this a little bit. If we look back at the way healthcare data has changed over the last few decades, we really see that it's exploded. I mean, if we go back 20 years or so, I think we had a lot of structured payment data with longitudinal episodic-based records of what was happening to patients. Over the course of time, we basically enriched this with prescription data and lab data, and eventually as EHRs and EMRs took off, we saw more and more complex data, including discharge and readmissions put into there. Finally, of course, we're moving into an interesting period these days where you can bring in external data sources, socioeconomic data, for instance, about patients. You can bring in external sources like demographics, images, video, voice, all kinds of things can be brought to bear. We also have, of course, devices. We know about Apple and the new work they're doing around heart studies. I had the privilege of meeting with James Park, the founder of Fitbit, last year to talk about some work they were doing in the medical space, that there is a great interest in capturing biometric data for use in new kinds of analytics. Finally, with Illumina promising a $100 genome sequencing, that's coming up, I think, in the next month or so. It's supposed to be, right? With Illumina promising a $100 genome sequencer very, very soon, we can't ignore the fact that genomic data is going to be another possibility to be mined. So if you ask me, what can we use for doing deep learning in healthcare or machine learning more broadly in healthcare, I would tell you there are a huge, rich vein of data sources out there. The goal for you will be to figure out what gives you enough data points, what gives you enough certainty, what gives you enough clarity to actually use. If we'd say, how are we beginning to look at this within Optum, I would tell you that we're seeing opportunities in a variety of ways. One, at a very high level, we're beginning to understand people who may be at risk, and this can be defined in a lot of different ways, but machine learning can help us understand where risk exists so that we can intervene in people's lives. Secondly, we're understanding better the factors that are driving change. These can be positive changes, which we may set out to reinforce in others, or these can be negative changes where we try to figure out how to mitigate the situation. Finally, machine learning is also allowing us to fill in some gaps where data be missing. So we were able to strongly correlate certain characteristics in a certain patient population. Even if all the data is not there, we can sometimes make an inference using machine learning that we wouldn't have been able to without. So with that, I would like to take you into a couple of very real world and very practical projects that we have ongoing at Optum. The first is around opioid use disorder, or OUD. Everybody here, I'm sure, is familiar with the challenge. Since 1999, the number of opioid prescriptions has more than tripled in the United States, as has the number of opioid deaths. It's a national emergency. It's a national crisis. So one of the questions that we have been asking is that of how can we mitigate this problem without taking away much needed pain medications for people who have real needs for this. So fortunately, within Optum, we have access to around 120 million patients worth of data. And so we began last year taking a slice of this patient data and saying, okay, what can we learn about people who became addicted to opioids, who became abusive to opioids? And we began to develop theories and develop models. And so we moved on from that thin slice. We found the next cohort, and we applied our model to that cohort, and we refined our model again. And we took another slice and another slice through all these cohorts and refined our models repeatedly. So where did we end up? Well, we ended up in a place where we have a pretty good idea based on all this training that we've done who is at high risk of abusing opioids. And in fact, the model has a positive predictive value of 82%, meaning that for that class of people in our system that we think are at the highest risk of abuse, what we've seen is that 82% actually do go on within the following year after we identify them. 82% go on to experience OUD. Just to give you a little bit of background on some of the things that we discovered, certain procedure codes, certain diagnoses more closely related to OUD than others. There were age and demographic information. So, for instance, people under age 18 or over age 60 are more likely to fall into patterns of OUD. And some things that should be no great surprise, people who frequent more than one doctor, go to more than one pharmacy, or people who have past histories of other substance abuse, including alcohol, marijuana, etc., are more likely to fall into this. So this is all intellectually interesting, but now we get into the really, I would say, fascinating possibility. If you wind the tape up to today and say we're now at time T0, you can look at our records and we can say how many people do we have in our system that are currently being prescribed opioids, and the answer is several hundred thousand. And then we ask the question, based on everything we've learned, how can we intervene in the lives of these patients to minimize the chance of them developing OUD? And so, again, we're embarking on this next phase of the journey. Some of it may involve working directly with patients. Some may involve working with caregivers. Some may involve working with pharmacies. It could be combinations of the above. The good news is that as we work to intervene in their lives and create better outcomes, we're also creating data, and that data can be subject to examination under machine learning models as well. The other thing I would point out is that these same techniques can be used for other addictions, but they can also be used for managing, say, chronic pain, and there's other applications here for machine learning models. That is one example of practical work that we're doing. A second practical example is looking at ways to reduce readmissions. So roughly 1 in 4 Medicare patients who are hospitalized are actually readmitted to skilled nursing facilities within 30 days. And so we began looking at the factors contributing to this and looking to see if we could categorize patients and better shape their care and also better pair them with facilities when they were, in fact, hospitalized. And we have developed an approach that results in about a 5,000 person per year reduction in readmissions. So I know 5,000 people doesn't seem like all that many, but we can look at it at one level and say, well, that's roughly $200 million a year that we're saving by reducing these readmissions. But I would argue the most important factor is that now we are improving the well-being and the quality of care for these 5,000 people, again, using machine learning. So at a very broad level, I would tell you that there are all kinds of opportunities here that we're exploring, some that I can talk about, some that I can't, but there's a lot of opportunity around improving diagnoses, particularly with anything in medical imaging. There's a lot of EHR analysis that's ongoing, including diagnosis, prediction, best course of treatment. We've been doing some work around deep learning for AI assistance. So for instance, with frail postoperative patients who go back home or aging in place scenarios, the ability to provide additional level of guidance and care and interaction, say through an Amazon Alexa or a Google Home that is customized to that person's individual needs, offers some really interesting possibilities. Additionally, we have begun looking at ways to identify patients with rare and underdiagnosed conditions. We're looking at ways to reduce the number of ED visits through predicting and intervening with patients at risk. And also, of course, with the boom in genomics that is currently ongoing, we think there's tremendous potential here. In quick and closing summary, I would tell you that the applications and use cases for deep learning and machine learning more broadly in the healthcare sector are really only limited by 2 things. 1 is your imagination, and 2 is the data. The good news is that the data is increasing by the month, by the quarter. And so that ceases to become a problem over the course of time, which leads us to our imaginations to figure out ways that we can apply these concepts, again, to change people's lives. Let me wrap up by showing you some resources. This is focused on things here in Charlottesville, places you can go to learn more. But I would tell you that wherever you are listening to this, there are undoubtedly similar kind of opportunities in your hometown. There are data science meetups. If you go to the one here in Charlottesville a year and a half ago, it would have 30 people. Today, it routinely has upwards of 150. So because of the explosion and interest in data science, it's really spreading like wildfire. There's a lot of online education. You can take courses through Udacity, Coursera, other educational providers. You can also take courses through machine learning service providers, sometimes at no cost. If you want to get in and start figuring out how to actually do something practically, start turning some knobs on your own, you can do so. Here in Charlottesville, we have two other resources. TomTom Fest, starting in 2017, actually had a machine learning mini conference, and that's expanding out next year. And then finally, my neighbor, Don Brown, runs the UVA Data Science Institute, and they're doing some really great things, including guest lectures and distinguished lectures at the DSI. So there's places to go to learn more information, and with that, I'm going to take a deep breath, grab a drink of water, and see what questions you happen to have.
Thank you so much, Rick, for that fascinating talk. So for the people who are logged in live on our webinar, if you'd like to send in a question, please submit it via the chat function. I'd like to start our Q&A session off with a general question. So you've provided some really interesting examples of how machine learning can be used on medical statistics. Could you talk a little bit about how you think machine learning may be able to interface with medical devices like focus ultrasound?
So how might machine learning interface with medical devices? I would say that there are opportunities both on the back end, think of after data is collected, but also on the front end. One of the great areas of exploration right now is called often machine learning on the edge. And let me give you an example of why this is important. If you're doing something like video processing, for instance, it can be very expensive and sometimes prohibitive to try to move massive amounts of video information up to the cloud for analysis. And so the more information we can begin processing on the edge in our instrumentation, then the better off we are. This means several things. One, it can cut cost by doing some of this processing on the edge. But secondly, it allows us to take our equipment, our devices, into environments where high bandwidth is not necessarily available. And so I would argue that as we begin to do increasingly sophisticated processing on the device itself, these devices become more and more portable. You're able to move them into areas where the supporting infrastructure may not be there to support the legacy embodiments.
Wonderful. Thank you so much. Do we have any questions from the room here?
Where do we stand in the U.S. versus China?
What an excellent question, Neil. Where do we stand, U.S. versus China? I would say that you can address this at a variety of levels. If you look back at machine learning and AI papers that were presented at conferences, say 6 or 7 years ago, they were almost entirely from the U.S. As of about 2 years ago, the papers coming out of China surpassed those in the U.S. And in fact, there was, I believe it was in 2016, a major AI conference that was being held in the U.S. that coincided with the Chinese New Year. They ended up having to reschedule this U.S.-based conference because so many of the people coming were arriving from China. Now, China is actually turning out, by the numbers I've seen, more papers than we are. China has also made this a matter of great national importance. When I say this, it's machine learning and AI in general. They want to master this. And if I look at who the biggest players are in this space, of course, American companies come to mind, companies like Facebook, Amazon, Google, but Baidu out of China is certainly leading the pack. In fact, Andrew Ng, who did the seminal paper on deep learning using GPUs, was teaching at Stanford. He went back and he led the deep learning projects for Baidu for a number of years. He's just recently moved on to new ground. But I would tell you that I expect many of the breakthroughs we'll see in the coming years to be coming out of China. This can be analyzed in a variety of ways. I think at one level, innovations that are distributed around the world help all to varying degrees. However, there will be certainly economic benefits and even military benefits to those nations that manage to really capture the lion's share of capability in this space.
Thank you so much. This concludes today's webinar. The slides and presentation will be available online on our website in the next few days. Thank you again to Rick Hamilton, and thanks to all for joining us today. Stay tuned to our newsletter and website for invitations to future webinars.